Hello. In this lecture, we will continue our discussion of authentication. So, recall that AP 4.0, the protocol which is shown in this figure, this is vulnerable to the server database reading attack, which we discussed in the previous lecture. It has another weakness, that is Bob authenticates Alice, but Alice does not authenticate Bob. That is, Bob is able to verify whether it is indeed Alice on the other side, but Alice is not able to verify whether it's indeed Bob on the other side. So, if there is an intruder on the path between Alice and Bob, then the intruder can intercept the I am Alice message, and the intruder can send any number R to Alice and ignore her response KBR. Alice thinks that she is communicating with Bob. So, this is a one-way authentication protocol. Alice authenticates herself to Bob, but Bob doesn't authenticate himself to Alice. Now, suppose Alice and Bob have a shared symmetric key KAB. How can we modify this protocol so that it achieves mutual authentication, that is, Bob authenticates Alice and vice versa. So, both the parties must authenticate themselves. So, we require mutual authentication. So, one way is this, after Alice sends the message I am Alice to Bob, we simply do an authentication exchange in each direction. So, we just repeat the protocol we use for one-way authentication in each direction to achieve mutual authentication. This shows the protocol. Alice sends I am Alice to initiate the authentication. Bob sends a challenge R1 to Alice. Then Alice sends a response to the challenge. Depending on which protocol out of the ones that we discussed in the previous lecture we are using, this FKBR may be KAB of R, that is R encrypted using the key KAB, or HR comma KAB, that is the hash of R concatenated with KAB. In either case, it is a response to the challenge which demonstrates that the responder has knowledge of the shared secret key KAB. So, FKBR is either KAB of R or H of R comma KAB. So, in either case, it demonstrates that Alice has knowledge of KAB. So, Bob sends the challenge R1 to Alice, and Alice responds with her response F of KAB comma R1. So, this proves that it is indeed Alice on this side. Now, Alice sends her challenge to Bob, that is R2, and Bob responds with his response to the challenge FKAB of R2. So, regardless of how we select FKAB of R from among these alternatives, the protocols achieve mutual authentication. This second version, where FKAB of R is H of R comma KB, has the advantage that it does not require encryption and decryption. So, it is computationally more efficient than the first version, where FKBR is KAB of R. This is one technique to achieve mutual authentication. We just repeat the one-way authentication protocol in each direction. Now, this protocol that we just discussed is inefficient because it uses 5 messages. So, we can see that there are 5 messages used in this protocol. So, it has a lot of communication overhead. A modified version that uses only 3 messages, that is shown in this figure. Alice sends I am Alice along with her own challenge, that is R2 to Bob. So, R1 and R2 are nonces. Then Bob responds with the response to Alice's challenge, that is FKAB of R2 along with his own challenge, that is R1 to Alice, and Alice then responds with her response to the challenge of Bob, that is FKAB of R1. So, is this modified version secure? At first, it looks like it's similar to the protocol on the previous slide. Alice sends a challenge, Bob responds to it, and Bob sends a challenge and Alice responds to it. But this protocol is not secure. It is vulnerable to an attack known as a reflection attack. We will discuss the reflection attack on the next slide. Suppose it is possible for a client to open multiple sessions to a server. This is often possible. For example, we can open different web sessions to the same server. Then an intruder 2D can fraudulently authenticate herself as Alice to Bob as follows. First, 2D initiates a mutual authentication as in the above 3 message protocol. So, this is the mutual authentication session initiated by Trudy pretending to be Alice. Trudy sends I am Alice along with Trudy's challenge R2 to Bob. Bob computes FKB R2, that's the response to Trudy's challenge, and sends it along with his own challenge R1 to Trudy. Now, Trudy does not have the secret KB to respond to this challenge R1, so Trudy is unable to compute f of KB comma R1. But then when Trudy receives R1 comma f of KB R2 from Bob, Trudy initiates a new session by sending I am Alice comma R1, where this R1 is the same as this quantity, which is Bob's challenge. Now Trudy sends it as her own challenge to Bob. So Trudy sends I am Alice comma R1 to Bob, and then Bob computes FKB R1 and then sends it to Trudy. Trudy then abandons this second session and goes back and uses this FKB of R1, which is sent by Bob, to complete this first session. So Trudy sends FKB of R1 to Bob, and hence that's a correct response to Bob's challenge. So Trudy's authentication as Alice is successful. This attack is known as the reflection attack. Using this, an intruder can authenticate themselves as Alice to Bob. So this is known as the reflection attack because when a challenge is sent by Bob to Alice, then if there's an intruder Trudy in place of Alice, then they can just reflect that challenge. So here is the reflected challenge. So Trudy just reflects that challenge, the same challenge R1 to Bob, and Bob himself provides the response to the challenge. So hence this is known as the reflection attack. So hence this protocol that we discussed is vulnerable to the reflection attack. So what are some defenses against the reflection attack? One defense is we can use different keys to authenticate Alice to Bob and to authenticate Bob to Alice. So far we have assumed that the same key KAB is used to authenticate Alice to Bob and to authenticate Bob to Alice, but we can use, say, different keys, maybe say KA to authenticate Alice to Bob and KB to authenticate Bob to Alice. So we can use different keys to authenticate Alice to Bob and Bob to Alice. So if this is done, then the reflection attack does not work. So the previous protocol modified with the fact that different keys are used to authenticate in the two directions. So that protocol works correctly. Another defense is when Alice sends I am Alice comma R2 to Bob, Bob responds with R1 comma FKB R2 comma Bob, where this Bob is Bob's identifier, and Alice responds with FKB R1 comma Alice, where Alice is identifier. This mechanism also works. So in this case, Trudy cannot reflect Bob's challenge because of the presence of the identifier in this quantity that is used to compute the function f. So this defense also works correctly. So using one of these defenses, we can defend against the reflection attack, and we can go back to this protocol which uses only 3 messages. Yeah, so this protocol which uses only 3 messages can be used along with the 2 defenses that we discussed, one of the 2 defenses that we discussed, and either of those defenses will defend it against a reflection attack. Now let's discuss mutual authentication using public keys. Suppose Alice and Bob know each other's public keys. How can we perform mutual authentication? So we can perform it as in this figure. Alice sends I am Alice along with R2 of Bob to Bob. So this is Alice selects a nonce R2 and encrypts it using Bob's public key, and the result is R2 Bob, and Alice sends this to Bob. Bob decrypts R2 Bob using his private key to get R2 and sends it to Alice. Bob also selects his own challenge R1, encrypts it using Alice's public key. The result is R1 Alice, and Bob combines R2 and R1 Alice and sends them to Alice. Alice then decrypts R1 Alice using her private key and sends the result R1 to Bob. So this protocol successfully achieves mutual authentication. Alternatively, Alice sends I am Alice along with a nonce R2 to Bob. Then Bob responds with R2 signed with his private key, along with his own challenge R1. Then Alice responds with R1 signed with her own private key. So this protocol also works correctly. So are these protocols vulnerable to the reflection attack? No, they are not vulnerable because Alice and Bob have different public key private key pairs. So because of this lack of symmetry, the reflection attack does not work. So when Bob sends a challenge to Alice, Alice cannot use the response of Bob to her own challenge to respond to Bob's challenge because the secrets used in the two directions are different. So Alice's private key is different from Bob's private key. So hence, this protocol is not vulnerable to the reflection attack. So both of these protocols are secure against the reflection attack. Now, notice that the above protocols use 3 messages for mutual authentication. Suppose Alice and Bob have a shared symmetric key KAB and approximately synchronized clocks. Can we modify the above protocol based on shared symmetric key so that it uses only 2 messages instead of 3? So can we use the fact that Alice and Bob have approximately synchronized clocks to reduce the overhead from 3 messages to only 2 messages? So mutual authentication can be performed as shown in this figure. Alice sends I am Alice along with FKB comma timestamp to Bob. Now Bob responds with FKB comma timestamp plus 1. So this FKB comma timestamp demonstrates that Alice knows the secret KAB, and this message FKB timestamp plus 1 demonstrates that Bob knows the secret KAB. So notice that Bob sends FKB comma timestamp plus 1 instead of FKB timestamp because FKB timestamp has already been sent over the communication channel. So anyone who sniffs the channel knows this FKB timestamp. So it doesn't make sense for Bob to just send the same quantity. So hence, Bob increments the timestamp and sends FKB timestamp plus 1, which is proof that Bob knows KAB. Again, here this function f may be KAB of timestamp, or it may be h of timestamp comma KAB. Here are alternative schemes. Alice sends FKB comma timestamp comma Alice, where Alice is identifier, and Bob sends FKB timestamp comma Bob. So here in this protocol, we use the same timestamp for authentication in the 2 directions, but we use the identifier of the sender to break the symmetry in the 2 directions. So the messages sent by Alice and Bob become different, and hence each one can demonstrate that they know the secret KAB. Alice and Bob use the same timestamp but different keys. That's another scheme using which they can mutually authenticate themselves. So actions similar to the ones that we discussed for one-way authentication using timestamps must be performed. For example, Bob must check that the timestamp used by Alice is within an acceptable clock skew, and Bob must remember the timestamps used by Alice in the past until they expire. So we discussed one-way authentication when Alice and Bob have approximately synchronized clocks. So the principles that we discussed in that context, they are also applicable here. Now suppose mutual authentication is performed as in this figure shown here. Alice sends I am Alice comma f of KAB comma timestamp to Bob, and then Bob sends FKB comma timestamp plus 1. One attack on this is that an intruder, say Trudy, can later on use this value sent by Bob, that is FKAB comma timestamp plus 1, to authenticate themselves as Alice to Bob, or to another server that shares the same key KAB with Alice. In this authentication, Alice sent the message FKB comma timestamp to Bob. During this authentication, Trudy eavesdropped on the conversation and intercepted FKB timestamp plus 1. Later on, Trudy sends the message I am Alice comma FKB timestamp plus 1 to Bob. So that timestamp is different. The timestamp used here is KB timestamp plus 1, which is different from timestamp. So the message is different. So if Bob checks whether the timestamp used is the same as in a previous authentication, then Bob will find that it's not the same timestamp, it's a different timestamp. So Bob may accept the authentication. So this is one attack which can be performed. Or 2D can intercept this message and use this value to authenticate herself to another server that shares the same key with Alice. So a defense against the above attack is the following. Alice sends fkb timestamp Bob, where Bob is Bob's identifier, and Bob sends fkb timestamp Alice, where Alice is Alice's identifier. Also, Alice does not use timestamp again to authenticate to any server. Since the server's identifier has to be appended to the message before finding the function f, this message will become different for different servers. So even if 2D records the messages being exchanged between Alice and Bob in this conversation, those messages won't enable 2D to authenticate to another server, because there the server's identifier would be different. But notice that this fkb timestamp Alice has Alice's identifier. So 2D should not be able to use this to pretend as Bob and to pretend as some other server, say Bob Prime. And then when Alice tries to authenticate herself to the other server, Bob Prime, 2D can send this message, which was recorded from this exchange, to authenticate as Bob Prime. So to prevent that, Alice does not use the same timestamp again to authenticate to any server. This concludes our discussion of mutual authentication. Thank you.